My name is Kirsten Paul.
I'm Shweta Mahanti,
I'm Bilal Tulamirza.
I'm Haranya Kamdar.
and our project is the sensors and its application on the TJ glider. For our project, we decided to build an autonomous underwater vehicle, which scientists frequently use to long-term surveys to collect data on salinity, conductivity, pH, turbidity, and dissolved oxygen. We'll be adding all these sensors to our glider, which is a type of AUV, and collecting data on them. Our temperature sensor will be collecting data, and we'll be analyzing the climate change. Our conductivity sensor will be used to convert into salinity, which we will use to analyze the hydrological cycle, and the rest of the sensors will be used to analyze the healthiness of the ocean so we can determine a plan of action for the ecosystem.
Our research objectives are as follows. First, we will explore various types of sensors that we can include on our autonomous glider. Then, we will design and build the glider with the selected sensors attached. Then, we will calibrate the sensors and write an Arduino program in order to store the data that we collect. Finally, based off the data that we collect and analyze, we will be making a plan to improve and protect the aquatic ecosystems that we study.
The first sensor we will be talking about is the dissolved oxygen sensor, or DO sensor. This sensor measures the amount of gaseous oxygen dissolved in water, and the DO enters the water by either direct absorption from the atmosphere, rapid movement of water, or as a result of plant photosynthesis. Water temperature and volume of moving water may also directly affect DO levels. DO levels below 5.0 milligrams per liter cause great stress to aquatic life. DO levels below 1 to 2 milligrams per liter cause large fish kills in dead zones. Our DO sensor will give us data in milligrams per liter format and help us determine the health of the water. Our DO sensor will work in fresh, salt, and brackish water.
The next sensor we're going to be looking at is conductivity. As previously mentioned, we're not looking for conductivity data, we're looking for salinity data. So we're going to have to take the data and convert it. Our conductivity sensor measures conductivity, total dissolved solids, practical salinity units, and specific gravity of seawater. There are 3 layers. The first layer is the conductivity probe driver, which transmits an alternating current square wave at varying frequencies. The second layer is an analog signal processing layer called the convolution layer, and then the final layer is the operating systems and communications. To convert the data from conductivity to salinity, we're going to be using the practical salinity scale from 1978. The practical salinity is defined in terms of the ratio K15 to the electrical conductivity of the seawater sample at 15 degrees Celsius and pressure of 1 standard atmosphere. Converted to KCl when mass fraction of KCl is 32.4356 times 10 to the negative third at the same temperature and pressure.
The next sensor we'll be looking at is a temperature sensor. The temperature sensor is just one wire connected to a central microprocessor, which makes it efficient for the glider because there's no external power source needed. The temperature sensor can collect data from negative 55 degrees Celsius to 125 degrees Celsius. We decided to look at temperature because the ocean is very relevant to predicting weather forecasts, atmospheric model situations, as well as climate change because of its high heat capacity.
The next sensor we're looking at is depth. Our depth is measured using an absolute pressure gauge. We selected a free scale MPXHZ6250. Our range is 0 to 250 kilopascals or 0 to 36 psi. It reads 14.7 psi at sea level. Pressure increases linearly at a depth of 50 feet as the psi goes up.
The next sensor we'll be looking at is the turbidity sensor. The turbidity sensor measures the particles suspended or dissolved within water, creating a cloudy or murky water. It will also help us determine the healthiness of the water, and our turbidity sensor will work by transmitting a light through the water sample and measuring the amount of light scattered to determine the turbidity levels. Low values of turbidity indicate high water clarity, while high values of turbidity indicate low water clarity.
The final sensor that we will be covering is the pH sensor. pH is commonly known as a measure of a sample's acidity. More specifically though, pH is a measure of potential activity of hydrogen ions in a sample. So the reason we'll be including a pH sensor on our glider is because it has been shown that aquatic life is very sensitive to certain pH ranges. So by analyzing the pH data that we collect in aquatic bodies, we can more effectively create a plan to improve and protect the aquatic health of the ecosystems.
Thank you for listening.